Welcome to the video about the pi-enabled binary from PwnShop Chapter 1. My name is Clinical and I will be walking you through the different steps of pwning this binary. Let's start off with an introduction. Pi means position independent executable. So what does that mean? Well, that means that the binary has a different starting point every time we run it. This is randomized. Whereas a executable compiled without pi has the same starting point every time. Let's take a look at this through pwnchecksec. So let's run pwnchecksec on the pi disabled binary. Here we can see it says no pi and the starting address is 0x400,000. If we run the same command on pi enabled, we will see that the pi is enabled. This means that we don't know what the starting point will be every time we run the binary. This has some consequences when we're looking at the binary through, for example, object dump or GDB. So let's take a look at that. If we use object dump -d on the pi disabled binary, we will see outputs like these. This is the actual address of main, and this is the actual address of win, in hex of course. But if we use the same command on the pi enabled binary, we'll see something like this. So what do these values mean? Well, they are the offset from the base address of the binary. Since this address is randomized every time, object dump cannot tell us the exact address of the binary as it can on the disabled one, where it actually knows what the address is going to be before we even start the program. Let's take a look at this through GDB to inspect it further. So if we use GDB pi disabled first, let's break on main using the b main command like this and run the binary using R enter. You'll see here that this is actually the address of main. This will be the same every time we run the binary. Now let's open the other one where pi is enabled. We'll break on main like before, and this time we can see it's breaking on an offset rather than the actual address of main, because it does not know what the address of main is before we actually run the binary. So let's run it and we break on main. What I'll show you here is that each of these addresses, when we're working with pi binaries, will be 6 bytes. So 1, 2, 3, 4, 5, 6 byte. And okay, listen carefully. The 12 least significant bits are going to be the same. So that means these right here will be the same every time, but this will be random. So let's try and run it again. The address is still the same, but that's because GDB is actually helping us. When we run the binary normally, ASLR will be on, but because the debugger is being nice to us, it will show the same address every time. I can show you an example of what it will look like in GDB if we run the binary through our exploit script, where GDB will not be able to do this the same way. So let's open the xpl.py. I'll be using my Vim setup for this, but you can use whatever you want. So I'll go down here and set this context binary to pi enabled, then I'll write. Then we need to set a breakpoint on main again. Right now it's using C for continue. This is the arguments to our GDB script. So let's say b main right here, and we need to write again. But how do we start the binary from within Vim and also give GDB as an argument? As you can see, we'll need to provide that right here. Well, we do it like this. Go into command mode, which means type a colon down, as you can see down here, you need to do exclamation mark dot slash percentage. This will just run the binary in itself. Run the script in itself, which will activate the binary for us. But in order to give it an argument like GDB, we'll have to use spacebar and then GDB like this. It has to be in large letters like this. And let's type enter and see what happens. Okay, so it first breaks on start, which is weird, but GDB just does this when we provide an argument that is not continuum. So if we type C and then enter, then we get to a breakpoint in main. As you can see, now these are the same as before, but this looks a lot more random. So just to prove my point, we'll run the binary once more, and I'll show you that this should be different. So let's type Q to quit, enter, enter, enter. Go into command mode again, type arrow up, and this will show us the command that we just ran. Type enter again, C, enter, and now this is the same, but this is different. This was just to show you that GDB can mess with you if you're not quite sure what's going on, because maybe you've never experienced this before. So no worries. Okay, let's look at the source code before we start writing our actual exploit script. So I'll write quit. I'll just clear my terminal, type ls, and we'll see that the source code is provided in here. I'll just cat it here, pi enabled.c, and this will show us that the binary was actually compiled using no stack protector, which means that there is no canary. We can also verify this with PwnShop, but for now let's just look at the source code. We have a win function here, indicating that we should probably do a read to win, and then we have the main function down here, where we see we have a buffer of 32 bytes, and this is the last thing that will be printed before asking for our input from the file descriptor 0, which means from standard in. Then the binary will read 200 bytes from standard in into the buffer specified here. This means that there is a buffer overflow, and that's what we are going to exploit. Before the buffer overflow, the binary will leak the address of main, which is part of the exploit, which is what we're going to do to exploit the position independent executable. Because we can actually use this address to calculate the offset of the base address of the binary. Sorry, we can use this to calculate the base address of the binary because we know the offset of main. And I'll show you how to do this in a moment. This will be crucial in order for us to exploit this binary. If we could not do this, we would have absolutely no idea where to find the win function, and we would have to randomly try an address again and again until we eventually got it, but it would not be a very reliable exploit. So let's take this folder here, open XPL again, and let's just run the binary like this. Okay, get a leak here. Before we start calculating the offset, let's just handle this first. So we know that this last part that's printed right before us, it gives us the address of main in hex. So Control Shift C to copy that right here, Control C to exit, and then type enter. Then we go down here. Now we're going to use some PwnTools functions in order to interact with the binary. So we're going to use the receive until, and I put this B before because it's bytes. Otherwise PwnTools will start telling us that it's assuming bytes because we typed in ASCII characters. So we might as well just give it bytes from the beginning. And we have to receive until this main : space 0x like this, and then I'll say pi_leak is equal to io.receiveLine dot strip. And I do this because I found receiveLine to be more reliable than the receive function. This however will append a new line to our input, and we would like to remove that. That's why we're using strip. So I'm stripping the trailing new line from what we just received, and I'm also saying that this is a byte. This new line is coming in as bytes. Make sure to use it like this and not like this. The reason for that is that strip will remove spaces and new lines. Sometimes, if you look at an hex to ASCII table, you'll see that the space is something like this. So if the address contains that character, then it will be removed by strip, and we don't want that because then the address will be messed up. So we'll do like this. Then let's just print this pi_leak just to see what we're working with and if we did this correctly. So just write, and then I'll just run the binary again like this. Okay, let's see what happened here. Oh, I typed it wrong. So receive line. Run it again. Sorry, my spelling is bad. So let's do it like this. And now we'll see that we are printing the address here. And that's good. So what we do now is we actually have to typecast this leak into a Python integer so that we can work with it and subtract the offsets of main, calculate the base address, then add the offset of the win function, and this way we can calculate what the actual address of the win function is during this exact run. So what we need to do is we need to type pi_leak is equal to, typecast it as an integer, pi_leak, comma 16. And this is 16 because hex is base 16. If the binary were to print this address of main as a decimal integer, we would have to use 10 because decimal integers are base 10. So for now, do it like this. Then we also have to print it to the terminal, just so that we can verify that we actually got the address of main correctly, and we're not working with some integer that we interpreted wrong. So we use log.info, and we write pi_leak. We can actually write main like this, %s, percentage again, hex, because now it will be an integer and we need to print it as hex. So we write pi_leak here, and then we run the binary with GDB like this. Continue to main, and then we see here that it's saying leaking pi address of main. So that's going to be this printf call right here. Let's put a breakpoint here, and then we'll see if this is going to be correct. This will also show you some interaction with PwnTools and PwnDBG. So let's do like this. To specify an offset within main, you have to use asterisk and then main, like this, main plus 57, right, and then rerun it again. Continue, and now if I type enter, GDB will interpret it as if I was pressing continue once more, so I don't actually have to type the C this time. So I can just type enter again, and now you'll see that the code has passed this printf call right here, and that main has been printed. Let's verify that this is correct. So type p for print main, and this will show us the address of main. We can see that this looks pretty correct. So, what do we need to do from here? Well, we need to calculate the pi base. Because if we know the base address, I showed you before with object dump, then we know all of the offsets of the functions, and this enables us to calculate the actual address of the functions during this run. But what is the base address, and how do I figure out what it is, where it is? If we use vmap, virtual memory map, enter, this will show us the layout of the binary. Here you'll see that there is some libc, here is some linker, down here is the stack, up here is the heap. The stack, for example, you can see is readable and writable, but not executable, since that would not be very good protection wise. This section right here is the .text section of the binary, and what you'll see here is that it is readable and executable, but not writable, since this would also be very insecure. Up here is the .data segment of the program, which you'll see is readable only. As you can also see here in the color coding, read-only data. So, this address right here is the base address of pi. This address right here is the base address of libc. And introducing in Ubuntu, I think it's Ubuntu 24, they also made the linker have its own ASLR. So this is the base address of the linker. So this is the size field. This shows us that this section is 0x 1000 bytes in size. Okay, we need to figure out what this address is while our exploit script is running. How can we do that? Well, we just leaked a pi address, which was main. So if you do p main, you can do this. We have to take this and subtract this from the address to figure out the offset of main. We could also use the output from object dump, but I like to use GDB since that's just what I'm working with all the time. For addresses like this, I like to use p/x, which means print in hex. And now since I've marked this, I'll use Control-Shift-C, Control-Shift-V to paste it, copy and paste it. Then I'll do a minus. I'll take this right here, Control-Shift-C, Control-Shift-V, and now I'll type enter. And this gives us the offset of main. Let's just take this, quit, go back into our exploit script, and then I'll write it here. Main off is equal to this right here. I'll write, and I'll go right back into our binary. I'll type C and go through until we reach the point right after the print. Then I'll open this again, and since I know that we're going to target a win function, I'm going to type p_win, and I'm going to do the exact same thing here. p/x win minus this address right here. Like this. So this is the offset of the win function. Let's take this and quit. I'll type win off is equal to the address that we just calculated. Okay, now we're going to calculate the base address of the binary inside of our exploit script. We'll do this since we know that main was leaked and we know the offset of main to the base address. So we'll say pi leak, which in this case was main, minus main off. But we also need to put this in a variable. I'll just call it pi base. Then we'll log this to the terminal to verify that the calculation was correct and that we can continue working with our exploit. Like this, and then I'll run it in GDB again. I'll just continue right after the printf, and now it shows us that it has calculated the pi base. Let's open VMMap just to make sure. You can see here 2175000, 2175000, that this looks correct. That's very good. Now, just to make sure, let's also add the win offset to this and check that we also calculated this correctly. So let's say win is equal to pi base plus win offset log.info win. You don't actually have to put spaces here, I just do it so it looks nice. And before I start the program again, I also want to show you a trick. Since this binary is not stripped, which you will see if you use the file command, I'll just show you really quickly here. File pi enabled. You'll see here that it's not stripped. This is actually what enabled us to do b main p win, because there are symbols within this binary. I'll use this command to open vim again, since this will execute my last command that began with a v, just so you know. Now I'm back in my exploit script, and I'll show you how we can use these symbols I just talked about to do our scripting a little bit easier. We can set the base address of the binary when we have leaked it and calculated it. So we can do, since we called this variable right here elf, we can do elf.address is equal to pi base. This enables us to look for functions using PwnTool. So we can do, let's just call this win1 is equal to elf.symbols like this, and then win, since we know that there is a win function. And let's just print this just to show you that we can actually use this as well. Log.info win1 and I'll continue down past the printf again. We'll see here that the win and that the win1 are exactly the same. And I also promised you that we had to print the win address just to check that we actually calculated it correctly. Here you can see 71C9, yeah, it looks pretty correct. Okay, that's good. Now let's continue to the buffer overflow. How can we figure out how many bytes we need to write? Well, at first glance you see that the buffer was 32 bytes and there is a RPP value, and let me just show you something. Stack addresses can contain 8 bytes of data here. So even though it only shows 6 bytes here, if we take this address and we inspect it, you'll actually see that there are 2 null bytes here to pad it. So it's actually 8 bytes in total here. You just can't see the null bytes. Okay, so we know that the buffer is 32 bytes. We take this value and divide it by 8. So if we can use p in here for print, take 32 divided by 8. Okay, so we have to fill 4 of these slots with data. But let's also remember that there is an RPP value right before the stored return address. Okay? So let me take you down to the read call in this binary and let's inspect further. So we use this command, next instruction, and I just type enter, 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 until I reach the read call. You could also set a breakpoint here from the beginning and then just continue until you hit it. That would also be very convenient. So we see the read function is being called here with the file descriptor of 0, meaning standard input. This is the address on the stack where it will start reading to. and this is the number of bytes that it will read. We can also verify this by looking at the register values up here. We see that RDI, which is the first argument to a function call, is 0, just like here. We see that RSI, which is the second argument to a function call, is here. These are the same. And we see that RDX is the same value as down here. Okay. Now let's calculate the distance from the starting input of read here and until we can overwrite the stored return address. So we can use the stack command with stack 20 to inspect 20 stack addresses like this. But how do I know which one is the return address? Well, you can use the info frame if like this, press enter, and this will show that the RBP is stored at this address right here, and the RIP is stored at this address right here. So let's look for this. Since I've done this a couple of times before, I'll know that this looks a lot like a return address in main, since main will return to libc start call main plus 122, where it will terminate the binary. Okay. F7A8. Let's verify that. F7A8. Yes, that looks correct. Okay. So we'll take this address, and now let's calculate the number of bytes that we'll need to overwrite the buffer. So type P, and then copy and paste the address using Control-Shift-C, Control-Shift-V, space, minus. And I always do these buffer offsets in just normal decimal, so I don't confuse myself with a binary address. And then let's take this, Control-Shift-V, Control-Shift-C, Control-Shift-V, and then we press enter. And this shows us that we need to write 56 bytes into our buffer until we reach the saved return address right here. Okay. I just wanted to show you this method of calculating the stack offset, because when, for example, the binary has canary enabled, this is a lot more effective than trying to just input a cyclic output, let's say cyclic 200 for example, because this might just result in you getting the message stack smashing detected, terminating, and that won't tell you the offset at all. So this is just a more clean way, I think, of calculating the buffer offset. So now that we know that the offset is 56, let's go back into our exploit script. I'll type quit, enter, and then we need to send the binary some data. As I showed you in the beginning, the binary will print these two characters here. So I'll do, before we do anything, let me just write the offset right here, equals 56. So now that's out of the way. As I showed you in the beginning, the binary prints these two characters right before asking us for our input. I made the binary this way just to be nice, so it would be nice and clean to make an exploit script for it. So what we'll do here is io.receive until, and now we know that the binary is going to expect us to give it some input. Since we saw that the binary was using the read function, we don't have to use the sendLine command, because sendLine will append the trailing new line, and this is only necessary when using functions like, for example, if gets, which likes a new line character when terminating. So let's just use io.send, and then we have to send something. I like to call my payload P, just because it's easier to type when you have to type it a lot of times. So I'll say P equals B bytes, let's just send it A's of offset, which was 56. Then I'll do an enter, P plus equal, just to append the next argument. And then we have to send it the win function, but we can't do just like this. We actually have to use struct.pack like this, And this is a PwnTools function that uses the pack function this is a PwnTools function. Let me say it like this. This is a PwnTools function that packs this to match a 64-bit address. So this will make sure that win is actually these 8 bytes long, as I showed you before when we were looking at the stack. So let's take a look at the exploit from within GDB, and then we can run it afterwards just to make sure that it's actually also working on the production environment. So let's run it in GDB. Let me type C, enter, and enter again. And now I just want to use next instruction and step through the binary. I actually want to step all the way down here, and now we can see there's no input here. We can see the return address as before. And now let's try next instruction here. Now we'll see that a lot of A's were written to the stack. Let's use stack 20 to inspect 20 stack addresses. Maybe I should make this window a little bit bigger so that the stack will be displayed a little prettier, like this. Now you'll see that it says that we wrote 8 A's to this address, and then it skipped the 6 next addresses. It did this because they are also filled with A's. A in hex is 0x41, so that's why you'll see this value here. Then we wrote the win address here, and just to confirm, I'll use the info frame command again, which says that the RRP value should be stored at C928, C928, which is right here, so we should be good. Let's use next instruction to keep stepping through the function, and then see where we return to. You'll see leave red, and we'll actually see that we are returning to win. And now I'll show you what it looks like when a shell is started from within GDB. This execute will start a new process with bin share with these arguments, and it'll look like this. Something looks like it crashed. But actually, if we go back here into our other terminal, it'll detach, and then we'll see that we actually have a shell. Now we can just quit this, and we have a shell right here. Let me just show you what it looks like when we're not using GDB. So I'll just Control C to quit, and then I'll just press enter, and I'm back in my exploit script. Let me just run it once more with no GDB argument, and we see that it worked again. That was all I had prepared for this binary. Thank you very much for watching.